Stairs. For thousands of years, the bane of robots everywhere. In this video, we're going to explore the challenges of footstep planning with a dynamic robot like Cassie. We also have some recent results we're excited to share with you and that will be included in an upcoming product. Lots of people have noticed that Cassie transitions from standing to marching in place and then starts walking. This behavior was inherited from Cassie's predecessor robot, Atreus, and is a consequence of optimizing for steady-state behavior. Cassie, like Atreus, is always actively balancing, and Cassie, like Atreus, lacks any outward-looking sensors and is effectively blind to the world. Many examples of complicated terrain can be easily navigated if you ignore the actual state of the world and treat all obstacles as gate disturbances. For example, Atreus could walk over obstacles by simply assuming that the world was flat. If this was a bad assumption, no big deal. The underlying gate dynamics were adequate to absorb the uncertainty. We've previously shown that Cassie can perform similarly. In this demonstration, Cassie is able to walk forwards, backwards, and sideways over an unknown obstacle without having any knowledge of the environment. Cassie thinks the world is flat, and the combination of passive dynamics and software control is robust enough for this to not matter. This sort of behavior is what allows Cassie to operate blind outdoors. Cassie doesn't need perfect knowledge of the ground to transition between different surfaces or to walk over roofs. In fact, this clip was part of nearly an hour of continuous walking on unpaved trails without falls. Unfortunately, at some point, the complexity of the world exceeds what the gate can accommodate, and advanced planning is required. We've been hard at work on this problem for a while, and we're pleased to share some recent results. We first extend our dynamic gates with planned footstep placements along the direction of travel. This allows a continuous transition from standing to multiple steps and back to standing, while utilizing the dynamic stability shown in the first half of the video. Notice that transitioning from standing to marching in place is no longer required. Next, the planner is extended to include the vertical direction, allowing individual foot placement in 3 dimensions. When the controller uses both legs and adds a smooth transition, Cassie takes a full step up. This behavior is dynamic. Cassie is unstable in the static sense at all times. This step height, 19 centimeters, is approximately what building code allows for stairs. And for the curious, yes, Cassie is attempting to maintain a constant pelvis height above the floor during this test. You wouldn't ordinarily do this in most circumstances. Finally, we extend this to an actual staircase, first with a single step, and then all the way to the top. This control framework combines the best traits of kinematic planning approaches and pure dynamics. Because no robots were harmed in these videos, here's 2 more clips from our test process. In this test, we told Cassie to take 2 steps up. There is actually only 1 step, but since Cassie is still actively balancing, she doesn't fall over. If you've ever gone up or down a staircase at night while not paying attention, you're probably familiar with how this feels. This is a great demonstration of how planned foot placement and active balancing are frequently at odds with each other when knowledge of the world is imperfect. Finally, we show that perception is still required in order to time the initial foot placement to the staircase. As our engineers say, this is when a spring-loaded inverted pendulum becomes a regular pendulum.